3G, question 13, optimization, straight out of the book. Here. So 2 corridors meet at right angles, 3 meters and 2 meters apart, 2 meters, 3 meters. AB, this is green line, is a thin metal tube kept horizontal. Well, that's so we don't go into 3 dimensions and make this problem even more difficult than it would be. Otherwise, it cannot be bent, moves around. So, okay, I think the problem's clear. It's like you've got to get this long metal tube through these corridors, right? It's like, what's the longest tube you could get to go around that corner? At some point there has to be this minimum spacing between the corridor walls to allow that tube to get through. As in, like if that angle was getting closer to 90 degrees, the tube could just come down and be really long, but then it won't fit through the corridors. Okay, so let's start the question. Now, split it up into 2 lengths. They want to know what's the expression for length of tube based on that angle and these widths. The way to do it is using little right angled triangles, right? Now you will need to know that that's also theta. Hopefully that's not too hard to see. I'm struggling to draw straight lines. It's corresponding angles. Because everything here is a right angle, this is a right angle as well. That's in the diagram. It's like that line's parallel with this line. Yeah. So that theta is like this one, and this theta is that one, corresponding angles. So we can say that that is theta. All right, then the 3 meters becomes an adjacent. The L1 is a hypotenuse. That means we need to go for cos. Adjacent on hypotenuse. Adjacent is 3. Hypotenuse is L1, well, not L2. I've called it L1. So with a bit of rearranging, L1 becomes 3 divide cos theta. L2, okay, let's have a look. The 2 is an opposite, means I need to go for the SO of SOHCAHTOA. Opposite on hypotenuse, hypotenuse is L2, opposite is 2, therefore the L2 length is 2 on sine theta. So my length expression is 3 on cos theta plus 2 on sine theta, and that gives me the length of the tube based on that angle and these corridor widths. So you would have to show some working out if you were getting marked on this. You can draw in little triangles on the diagram, do some working. I've erased my working because I'm going to run out of room. Now, when it comes to finding the derivative, I would rewrite it first. Cos theta to the minus 1. So before I start my derivative, I'm writing this so I can see, so I can make using the chain rule a bit easier. All right, so I think most of you would have used the chain rule, but just you don't need to go to quotient rule. Chain rule is going to be easier. So the derivative, let's use the correct notation. We've got outside minus 3, inside stays the same. Subtract 1 from the power. Now the inside derivative of cos is minus sine. Okay, now to this part, outside -1 times 2 minus 2, inside stays the same, subtract 1 from the power. Now look at the inside, derivative of sine is cos. So to tidy this up, -3 times minus sine, so we have 3 sine theta, right? That's on the bottom of the fraction, cos squared theta, minus 2 cos theta on sine squared theta. When does it equal 0? Derivative equals 0 when 3 sine theta on cos squared theta equals 2 cos theta on sine squared theta. So what I've done is I've imagined in my head that equals 0, and then I've added 2 cos theta on sine squared theta. I've added that to both sides. So it's ended up over there. But don't write the equals 0 with your derivative, because this derivative here, I'm probably going to come back to it. I want to have a nice derivative. I want to have the derivative in a easy to read form for future reference. Now, we need to keep going here. Let's times both sides by sine and sine squared, and times both sides by cos squared. So this is a little cross multiplication step. We'll get 3 sine cubed theta. I've got the squared times the sine makes cubed. 2 cos cubed theta. Now the book did actually give me a hint that I want to go to tan, and I can see how to do that. I know that tan is sine on cos, so I've divided both sides by cos to get it on the bottom of the sine. I've also divided both sides by 3. Need a bit more room. I need to explain why this is tan cubed. Let me do that first. So if I write sine cubed on cos cubed, that's the same as I'm rushing. It's not what I wanted to write. This is what I want to write. This, right? And that's the same as tan. So we can just say, let's go up here. You should be going down the page. We can say tan cubed theta equals 2/3. Let's cube root both sides. Tan theta equals cube root 2/3 theta equals arctan cube root 2/3. Hopefully I can remember that, because I now need a calculator for that one. Cube root 2/3. All right, lock it away, Eddie, and go to the calculator. So arctan, make sure your calculator's in radians. How about you go 2/3 to the power of 1/3. That's the cube root right there. Press math, you do it this way. There's your cube root. Cube root 2/3. Close all your brackets up. So we get 0.718 radians. 3 decimals is enough. 0.718 radians. Oh, I think the book reports it in degrees. So theta is approx 0 radians. Now, conversion on the calculator. It's going to be a bit hard to see. Let's just hide it. Take this number, times by 180, divide by pi. Divide by pi, 41.1 degrees. What's the book say? There it is, 41.1 degrees. Oh, they've got the whole expression there. So we've done it. We've shown that. Find L when we want to know what the length is. Comment on the significance. I think because it's optimization, we might draw the sine diagram as well. We want to be in the habit of doing that. So, are there limits to this, to that angle? I think there are. It's really, the angle can't be smaller than 0, and the angle can't be bigger than pi on 2. This is about 40 degrees, so it's pretty close to being in the middle. 0.718 radians. I'm doing a sine diagram of the rate of change of length with respect to that angle. Now let's test down in here. Maybe we use pi on 6. Oh, jeez. How about we just use 0? No, but then we have to divide by 0. Can't do that. Oh, that's annoying. So if I was going to test this properly, I'd be going back to the calculator, I think. What have I done for it? So what? 3 sine, making more work for myself. 3 sine, let's do pi on 6. And that was all divided by, now I can't read the original. Where are we? 3 sine pi on 6 on cos squared pi on 6 divided by cos pi on 6 all squared plus, or was it minus? I think it was minus 2 cos theta on sine squared theta. 2 cos pi on 6 divide, oh look, I forgot already, sine squared theta, oh yeah, that's right, sine pi on 6, it's a mess, isn't it? And that's all squared. Alright, now I'm just going to hide the, there we go, so I've done 3 sine theta divide cos theta all squared. I've chose 30 degrees, right, pi on 6, minus 2 cos pi on 6 divide sine pi on 6 all squared. That gives a negative. So let's put that on. Negative. That's going to be positive. Pretty sure. Maybe we could check it quickly. We have to hide everything though. But the good news is once you've entered something like this, you can just copy it. We want to be greater than 41 degrees What about if we go to pi on 3? So just find all the 6's, make them 3's. That's 60 degrees now. And I think that's a positive number, yep. That's a little confusing actually. We're finding a minimum length. But if you stop and think about it, it does make sense. It is the smallest length that's going to exist between those corridor walls. But it's also the longest length of tube that could fit through. So they, we still haven't even worked out the length, have we? The length would come from this. Let's write that down. Don't know how long it is. Length equals 3 on cos 0.718 plus 2 on sine 0.718, so it must be greater than 5. So it's 3 on cos, 2 on sine. Let's find out how long it is. 3 on cos, 0.718 plus 2 on sine, 0.718 radians, and that equaled 7.02 meters. Okay. It's not too bad, is it? So approximately, I can't even remember what I said now, 7.02 meters, right? Approx, 3 sig figs. Yeah. If you're in doubt, you're in the exam, you're thinking, are they going to pin me for only writing 3 sig figs? Well, tell them that's what you're doing. Then they'll be like, oh yeah, okay. We won't take a mark off. So to put it into words, the longest tube that fits, assuming the tube has no width, is infinitely thin, the longest tube that fits through corridors, which was sort of a little bit confusing because up here in the sine diagram you're finding a minimum, right? But if you think about the diagram, I'll go back to the picture. You can see that we're looking for this shortest path here between those corridor walls. So it does make sense that would be minimizing that length, and if the angle increased out to there, say, you know, maybe up to close to 90 degrees, the line would be going down there. This tube could be really, really long, right? So that might be why it's in red actually, because the sine diagram shows a minimum, but your brain's going to be thinking, what's the longest tube I can get through? Anyway, interesting question.